Let's talk about how to compute the dot product between two vectors. If we have vector v, which is x1i plus y1j, and w is x2i plus y2j, the dot product is defined as v dot w, that's why they call it the dot product, where you take the components and multiply them, so x1 times x2, and then add those together, so plus y1 times y2. This is a dot product of vectors. This is a dot for multiplication of scalar quantities. So remember, x1, x2, y1, and y2 are all real numbers. So when you do this, the result is a scalar quantity. You just get a number as the answer, so this is also sometimes called the scalar product. For example, for v equals 2i minus 3j, w equals 5i plus 7j, we compute v dot w, again, vector notation here, and we just take the actual numbers themselves, 2 times 5, plus negative 3 times 7. The result is just a single number, positive or negative, and you notice the i's and j's don't appear in this at all. They are part of defining the vector, but they are not at all related to finding the dot product. The dot product has several nice properties, the first of which is that it is commutative, where v dot w is w dot v, which is pretty obvious from the definition, because if you just reverse the order here, the multiplication is commutative and the addition is as well, although that doesn't matter. So that one is pretty easily checked. It is distributive in that if you have three vectors and you want to do u dot v plus w, that is the same as u dot v plus u dot w. And just think through how this works. If you add two vectors here, you're going to add the components, and then u means you'd multiply the x times the sum of those x's, and the y for u times the sum of those y's, so it works out this way as well. You can show that with a little algebra, but keep in mind what you have here. If you add v and w, you get a vector, so u dot a vector equals a scalar. Here, this dot product will equal a scalar. This is a scalar, so you add those two together, you get a scalar on that side of the equation as well. If you dot a vector v with itself, you get the magnitude squared. It's not super surprising because if you just work that out this way, the magnitude would be the first component's real part squared, and plus the second part squared. You would square root the whole thing for the magnitude, so if you square that, it's like the square root wasn't there. The third product is that if you take the zero vector dotted with vector v, you get the number 0. That's kind of a bookkeeping thing if you do anything advanced with vectors and dot products, which you can do a lot of math involving, I don't know, fields or something with them. Not really super important for this class, but the 0 vector is 0i plus 0j. So clearly when you dot product that with anything, it results in the number 0. You can derive a formula using the law of cosines for the angle between two vectors. If you have two vectors in a plane, there's always some acute angle between them. You wouldn't look at the obtuse angle around the other way, but there's always some angle between the vectors, and you can come up with this formula that relates them. The cosine of this angle is u dot v divided by the magnitude of u times the magnitude of v. Again, that's a dot product, that's multiplication. Let's just do an example. Here are our two vectors. Let's just put those into the formula. The dot product, we do 10 times 6 plus 1, think about that as a 1j plus negative 2, divided by the magnitude of u is going to be 10 squared plus 1 squared square root times the magnitude of v. I realize I just said things weird because this is u and v and this is v and w, but I'm using this as the first one and this as the second one. So I think you can follow along. So this is 6 squared plus negative 2 squared. And then if you put that all into a calculator here and do the inverse cosine of that, you end up with that theta is about equal to 24.1 degrees. And if you actually plotted these approximately, here's v, 10, and 1, and then w is 6 and negative 2. It's not drawn to scale exactly, but that would be 24.1 degrees. So the last fact we should talk about is that if two vectors are what we call orthogonal, which we had the word perpendicular before, which is usually used in 2 dimensions, but vectors can be 3, 4, 5 dimensions, whatever, and then you switch the word orthogonal for reasons that mathematicians understand better than I do at this point. But if 2 vectors are orthogonal, then their dot product is 0. And that just follows from the equation here. Because if they're orthogonal, that means the angle between them is 90 degrees, and the cosine of 90 is 0. So if this side equals 0, this side also has to equal 0. The denominator is never going to be 0, so that means the numerator has to be 0. So if you're ever asked to check if 2 vectors are orthogonal, just check if their dot product is 0. And of course, if 2 vectors are parallel, that means that theta equals 0 degrees. Or 180 degrees if they are anti-parallel, going in opposite directions. But then, of course, your calculator is only going to give you one of these out. It would give you 0, not 180. But either way, they're parallel either way. Whether they're going in the same direction or different directions, they're still parallel vectors.